Welcome back to the AI Research Roundup. I'm Alex. Today we're looking at EvoRL, a GPU accelerated framework for evolutionary reinforcement learning. Published in January 2025, this paper introduces a new framework, also named EvoRL. Its main goal is to speed up evolutionary reinforcement learning, or EvoRL, by running everything on graphics processing units, or GPUs, which are specialized computer chips. Evolutionary reinforcement learning combines reinforcement learning where AI learns from rewards with evolutionary computation, which uses many AI agents learning together. This EvoRL framework is the first to do this end-to-end on graphics processing units, making it much faster. It's great to see they've also released the implementation, so this GitHub repository hosts EvoRL, their JAX-based graphics processing unit accelerated framework, JAX. Well, it's a Python library for high-performance math, essential for getting that speed on graphics processing units. In the repository, you'll find the core library, configuration files for different agents, training scripts, and documentation. So a key architectural feature of this EvoRL framework is its hierarchical vectorization. This means it's designed to run many things in parallel, at different levels. Think of it like this. It can handle multiple simulated environments at once, multiple AI agents learning simultaneously within those environments, and even parallelize the training process itself. This multi-level parallelism is what really lets it take full advantage of those graphics processing units and the JAX library, making everything much faster. Alright, so building on that hierarchical structure, this next figure, Figure 2, it lays out the core components of EvoRL on the left, and on the right, the kinds of algorithms it can handle for policy search. Policy search, by the way, is just the process of finding the best strategy for the AI. We see components like the agent, which holds the AI's decision-making policy, and a sample batch, which gathers up experiences. Then, the framework supports not just standard reinforcement learning or evolutionary computation alone, but also hybrid approaches like evolution-guided reinforcement learning, where evolution helps the learning process, and population-based AutoRL, for automatically tuning settings. Okay, so after seeing the general components and algorithm categories, Figure 3 gives us a closer look at how some of these actually, work inside EvoRL. It shows specific training workflows. For instance, Diagram A illustrates how standard off-policy reinforcement learning might run, with steps like rollout, which is just the AI agent interacting with its environment, and then storing those interactions in a replay buffer to learn from. It also shows a separate path for an evolutionary algorithm. Then, Diagram B details a hybrid approach, specifically cross-entropy method reinforcement learning, or CEMRL, where population generation and reinforcement learning updates are more tightly coupled. And finally, C shows a population-based AutoRL workflow for something like population-based training, or PBT, focusing on evaluation and an evolutionary layer with mutation and selection to improve the AI models over time. So these diagrams really show the flexibility of the EvoRL framework in action. Alright, building on those workflows, Figure 4 really demonstrates EvoRL's speed with evolutionary algorithms. It focuses on OpenES, an evolutionary strategy comparing its average iteration time, so how fast each learning cycle completes. We see OpenES running in RLlib, which is CPU-based, versus EvoRL on a graphics processing unit. Across different settings, like population size, the number of episodes for fitness evaluation, that's how agent performance is scored, and the hidden layer depth or complexity of the AI's network, EvoRL is consistently over 60 times faster. The EvoRL with noise table line shows an even quicker variant. Okay, so now with Figure 5, we're looking at similar speed comparisons, but this time for different types of algorithms. We have cross-entropy method reinforcement learning in Part A, and population-based training in Part B. For cross-entropy method reinforcement learning, EvoRL is much faster than the official version, and also outpaces another framework, FastPBRL, especially as population size increases. You can see FastPBRL hits memory issues, but EvoRL scales well. Then for population-based training, which uses underlying reinforcement learning algorithms like proximal policy optimization, a popular method for stable learning, and soft actor critic. Known for its efficiency, EvoRL shows speedups of 30 to 40 times over RLlib or fast PBRL. And again, those other systems struggle with memory at larger populations, really showing off EvoRL's graphics processing unit-based design. Okay, so after seeing how fast EvoRL can run these algorithms, Figure 6 now focuses on their actual learning performance. It benchmarks different evolutionary algorithms, like ARS and OpenES, on several robotic tasks such as ant and half-cheetah. We're looking at the average return, which is basically the AI's score over training iterations. The plots show how performance changes with different AI network sizes and with how thoroughly each agent's fitness is evaluated. It's interesting because a bigger network, or more evaluation, doesn't always mean better final results across all tasks. Alright, so shifting from those performance graphs, Table 2 gives us a different perspective. It shows the total number of reinforcement learning updates, which is essentially how many times the AI models refine their strategies during the training of evolution-guided reinforcement learning, or ERL, and cross-entropy method reinforcement learning. This is for those same robotic tasks, like ant and half-cheetah. What's really telling here is that using a fixed number of reinforcement learning updates per iteration, as seen in the rows labeled fixed updates, dramatically reduces the total updates compared to dynamically scaling them. For example, with ERL on ant, it's 1.86 million updates versus 8.27 million. This reduction happens while maintaining or even improving performance, suggesting that a fixed schedule can be more efficient, especially in early training stages. This efficiency in updates we just saw in Table 2 really underscores the broader impact of EvoRL. It's clear that EvoRL, by smartly using GPUs, not only accelerates these complex evolutionary algorithms, but also offers more efficient ways to train our AI agents. This kind of framework can really open up new avenues for research, making it easier to tackle challenging problems in robotics and beyond. Well, that's all the time we have for today's AI Research Roundup. Thanks for tuning in. I'm Alex, and I'll catch you next time.